Morning. Okay, so welcome to the lecture. And in yesterday's lecture, which was in previous lecture, what we studied was something which is called a two-state Markov model. So again, here we only looked at two state, and because we defined them to be as one state was alive and the other state was dead, we know that it cannot really happen that you can come back from the dead state into the alive state again. So there was only one arrow in only one direction. So, but as we know, that's not the case always, right? Let's say if you are not looking at alive and dead, let's say if you're looking at healthy, sick, and dead, which is the model that we'll be studying in today's class, you can go from healthy to sick, and you can again move back from sick to healthy, or you can also go from sick to dead. So again, over there, once you reach dead, it is an absorbing state, right? You can never go out of that state. You will always just stay in there. So again, that's one thing. So in today's lecture, we will try to erase this two state, and we will look at only the Markov models. So again, we won't be looking at Markov chain, because now what we want to do is we want to create a version of not discrete time, but a continuous time. So to remember, I defined those kind of processes as Markov jump process. So again, we call it Markov jump because you don't know when you're going to take that jump, and it can happen anytime. And that is why it's continuous time. So one example could just be, the customers arriving at a particular restaurant. So you never know when a customer is going to come in. So to account for the fact that at this particular time, let's say a customer came, or this much was the time difference between two customers arriving, you will have to use continuous time. You can't go with discrete time. So that is what we are gonna study in today's lecture. And again, just to recall, we studied a bit of notations. So TPX is for the probability that if you are aged X today, the probability that you will survive up until at least T years next. So up until at least next T years. And again, you know that you can either survive or you will not survive. So if you survive, it's TPX. And if you do not, it's kind of TQX. So this is the probability that you will be dead by the time you are aged X plus T, given that you are aged X today. And as we know, these two are mutually exclusive and exhaustive. So they add up to 1. And then we studied some assumptions. And I guess just to remind ourselves, we studied that this mu X plus T is some transition rate. So again, whenever I'm talking about rate, I know it can be greater than 1. But when we talk about probabilities, we know they're bounded between 0 and 1. So always remember, this mu can exceed 1. But again, for us, when we're defining that this particular mu X plus T is constant, we define a particular time interval, and we say that only between 0 and 1, this mu remains constant. So for a very short interval of time, we assume that this mu remains constant, and if this mu remains constant, that is the time we concern ourselves with. What's the possibility that something will happen in a very, very short interval of time, which we define as dt sometimes. So dt is just a small change in t, dt. Okay, and then we had a look at how to figure out the probabilities. And I guess to figure out the probability, so our end goal was to derive the transition probabilities if we knew something about the transition rates. And we ended up having this thing as the conclusion. And again, if you let your mu to be just a constant, which does not depend on t anymore, then you will get this thing as your value of TPX, which is the probability that if you're aged X today, you will survive for the 3 years at least, next 2 years. And then we had a look at how do we derive the transition rate, because not every time we will know the transition rate as well, but we know that the information that we have is of the difference, is of basically the observation, the difference between when the observation ended for a particular life and the observation started for a particular life. So that we define as the total time spent under the observation, which is just VI. And then again, there are various things that can happen. So the actual time, the supposedly time for the observation, within that time period, a life could either die or a life could not die. So we define our indicator variable and we try to analyze their joint density. And then we try to somewhere basically use that to figure out our value for the transition intensity. And it is kind of intuitive. So what it says is, so this is the transition intensity of going from a live state to the dead state in a very, very short interval of time. So what we are doing is, we're just calculating the number of deaths that you have observed within some time upon the number of total time period, upon the total time period you have observed all the lives. So that will give you kind of the mortality rate or the transition rate that we were looking at over there. So I guess that was it about what we studied up until now. So today we are going to expand this thing. Let me just share another screen now. Yeah. So today what we are going to do is we will expand these models to more than 2 states. And we'll have a look at how do we determine the transition probabilities if the transition is possible back to a particular state, not only from one state to another, but also between various states using various sample paths. So, and I guess that will be useful for us in many number of ways to again answer questions like, what is the time period that you will stay healthy? What on average what time on an average do you expect to stay healthy? 1 or 2, I mean, what is the chance that you will move to sick state, let's say if you're healthy today, in so time, and again, so on and so forth. So there will be so many different questions that you can ask, which will be related to you as an analyst who wants to determine and know something about this particular policyholder using the information that they have provided to you. Okay, so I guess now that we have kind of defined this, so in this particular chapter, we will only be covering the homogeneous case. So to remind ourselves, whenever I'm talking about homogeneous case, what matters is not the time, not the exact time when I'm starting to make a transition from one state to another. What matters is just the time difference and some notation. So again, if I'm writing Pij here, it means I'm moving from I to J state in time S to time T. So sometimes if I write it like this, it will be that I'm in state I at time S and I move to state J at time T. This is what this notation says. But again, sometimes you might have different notations. So sometimes you might also see something like this, Pij S, S plus T. I guess this is much more easier to interpret because what we're kind of saying here is that this is S and this is, let's say, S plus T. So this T is the time interval in which you're moving from state I to state J. So again, these notations might differ. Sometimes when I'm calling mu as my transition intensity, it may not always be mu. It might be sigma, it might be mu. It can take any other Greek letter as well, depending on what the question tries to say you, or sometimes if you are looking at the tables, you might have in question, let's say mu, but in table booklet, let's say you have sigma. So don't be, surprised as in there is no value for mu in the table booklet. No, this represents transition rate and this represents transition rate. So they are one and the same thing only. It's just the notation that is a bit different. Okay. So now again, what we have written here is Pij, where we start at S and we ended up at state J in time period S plus T, which is within the T time span from state S. Okay, so now if I say that I'm looking at a homogeneous Markov jump process, So now if you see, we are talking about a Markov jump process. Previously, we were talking about a Markov chain. So the, just give me a minute. Yeah, so again, we have to remember the fact that we are looking at continuous cases. So that is why I'm not going to use the term Markov chain anymore. I'll be using Markov jump processes. So once that is clear, now again in this chapter, we will be looking at homogeneous Markov jump processes. And now if I'm saying that I'm looking at homogeneous, does it matter if I write S here? No, right? Because what matters is the time difference. And what is the time difference? It is S plus T minus S, which is nothing but just T. So that is what I can write here. Or else you can also write it as, so let us say if you are denoting here the time difference, you can write it as this. Or else you can also write it as 0 comma t. I mean, essentially the probability, the answer to this, the answer to this, and the answer to this is going to be one and the same thing. So this is how you can rewrite this if you're looking at homogeneous cases. But if you're looking at time in homogeneous cases, we know that it really matters whether you were at state I in time 0 or in time S. So it is no more that only the difference matters in time in homogeneous case. So I guess that is all that you need to know. And again, here and transition intensities will also have some subscripts where these will denote the transition of moving, let's say, from one particular state to another state. So I guess that was it about just some notation, which we all should be aware of before even starting to study this particular chapter. So, okay, as of now, we are at the 4th chapter, which is called time homogeneous Markov jump processes. Okay, so even before we study about Markov jump processes, let me take you guys back to chapter 1 or even the very first lecture where I discussed with you guys the Poisson process and the exponential process, right? And the exponential distribution. Do you guys remember the car example? I guess I gave a car example. But again, now what I'm going to do is I'm going to redefine the same process in some another manner. So the Poisson process can actually be defined in 4 definitions, all of which are true. And if any of those is true, we say that this particular random variable follows Poisson process. But again, now what we are going to have a look at is in terms of counting. So let us say we are at a restaurant. I mean, we are a restaurant company and we want to see what is the expected time that you would like to wait. I mean, what time do you expect there be in between the arrival of 2 customers, because you'll have to serve them, right? So again, the number of waiters that you might keep, these kind of decisions might be based on these calculations. So again, if it's a very small organization, you wouldn't really care, right? But then if it's a big and if you much more care about efficiency, then you might want to basically sit and do some analysis. So again, let us assume that is the case. And what we are going to do is now, let me define my NT. So I'm going to define some random variable NT here, which measures the number of, so this is going to measure the number of customers that arrive. So again, I particularly take this example because there is one inherent assumption in Poisson process, which you guys should always remember. And we'll come to that assumption. But again, for now, I'm just saying that I'm defining an NT variable, random variable, which measures the number of customers that have arrived in my restaurant. Okay, so let's say in a cafe. A restaurant is a very big word. So in a cafe, let's say, okay. So what I'm doing is I'm counting the number of people, right? 1, 2, 3, 4, 5, 6. But again, we know that whenever we go to a restaurant, let's say, or a cafe, we don't go alone, right? We go along with some friend or someone else. So what the very the very crux of this Poisson process is the fact that no two events can occur at the same time. So what that means is that more than one person entering the cafe is very, very unlikely. And I know that this example does really take into, does not really hold by that assumption, but maybe what you can just think is that the door at the entry of the cafe is very narrow, so only one person can step in at the time. And because you're looking at continuous time, what you can maybe imagine is, if let's say, even if you're a bunch of 5 people, you'll have to make a line and then entry one by one. So maybe you can just imagine that. But again, this is just to make you guys remember that this is one of the basic assumptions of this particular model. So now when I want to figure out what is the chance that I will observe some event happening. So whenever I'm saying event, the event is a customer arriving. So let me just define that. A customer arriving, and then this I'm defining, sorry. So this I'm defining as my event of interest. And this is the event that I care about. Okay, so now what's happening is you can define another random variable, which will just be, let's say, nt plus h minus nt. So what I kind of did here is, let us say I'm looking at some time interval. So I'm looking at some time interval 0 to t, and I have some observations here. I can just draw any crosses. So these basically represent, wait, how many students do we have in the lecture? Just let me answer some students. Just give me a minute. Okay, yeah. So when I'm saying that I'm looking at time spanning from 0 to t, and these crosses represent the events that I've observed. So basically the customers that have arrived. But again, now what I can also do is I can chop this one big time interval into some small time intervals. So let's say I define that this is my T1, then this is, let's say, my T2, then this is, let's say, my T3, and this is, let's say, my T4. So ideally, you would want to do this in equally spaced intervals, but again, that is not necessarily required in all the cases. But again, what now I'm concerned with is, what is the chance that I will observe one event happening in this particular time interval? So I define a very, very tiny interval after t, which is h here. And that is what I want to see. I've observed up until t, and now I want to figure out what all can happen in time t plus h, which is a very, very short span of time interval after t. So there are 3 possibilities that I see happening, and that can basically be summarized as either you observe 0 customers, that is the case wherein no customers enter, or you observe 1 customer, that is the case where 1 customer enters, or you observe more than 1 customers entering your cafe. Okay, so now what we want to do is we want to figure out the probabilities of all of this happening. So again, whenever I'm talking about Poisson process, I know that, let's say, I haven't mentioned it, so probably should. The parameter of my Poisson process is, let's say, lambda here. So I'm going to assume that this NT, which is just accounting. So, okay, whenever I'm saying about this NT, which is the actual random variable, and this is sort of, maybe I should write it here. This is sort of an increment, right? So if you go back to the definition of Poisson process that we studied in the very first chapter, it was something about the increments being stationary and independent. So we are going to make those assumptions again here. So we will assume that the events that happen, so the probability of people entering in the cafe, that is independent of any other person entering the cafe. And again, the stationarity is maintained. But again, that is another definition. So that will still hold true. But again, the way we are going to define here is a bit different. So what we will say is, we know that lambda is the rate at which we expect the customers to arrive at a particular cafe, right? So that my rate is lambda, and again, that is the instantaneous rate. Okay, that is not the rate of, let's say, that is a rate, right? Not a probability. So for, let's say, if I'm talking about probability, that I'm talking about a particular one-time step after. But when I'm talking about rate, it's instantaneous, it's in continuous time. So if I want to say that in h time period, so the difference here is just h, right? T plus h minus t. So if I here want to say that in my h time period, which is a very, very tiny small interval, if in that particular time period, I observe one customer entering my cafe, then how can I rewrite its probability here? So if I want to figure out the probability that I will observe one customer, I'll observe precisely one customer entering my cafe in h time period, how do you think I can write this as? Any guesses? So think of what's happening, okay? Lambda is the transition rate, basically. So when I'm talking about transition rate, the transition here represents the customer entering the cafe. So lambda is the rate at which customers enter the cafe in a particular instance. And here I'm talking about the time h. So what do you think is the probability that you will observe exactly one customer entering the cafe? Yeah. Anyone? Okay, let me frame it in another way. Let us see if I tell you guys that let me just frame it in another way. And again, let me just write it. So let's say if I say that my lambda is 5. Okay, so what I mean to say here is that I observe at least 5 customers entering my cafe per minute. Okay, so I'm saying that my lambda is 5. So each minute customers enter my cafe at the rate of 5. And what I'm asking you guys is, let's say I'm defining my, so my h time period is, let's say, 1 hour. Okay, so now what do you guys think will be the expected rate for customers to arrive within 1 hour if 5 is the rate per minute?
5 into 60.
5 into 60, right? And how did you arrive at that? I mean, so you took 5 from here and then you divided the, basically you did the number of minutes that you have within 1 hour, right? Which was 60. So you multiplied that with 60. So this is the similar kind of thing that you're going to do here. So we know that my lambda is the rate at which I observe one particular transition. Okay, but now I don't know what this conversion is, right? But I know for sure that this lambda that I've defined here is very is, just for instantaneous time, right? Like in not even a moment, it's like one particular instance. So when I'm defining my h in terms of this particular instance, it just gets multiplied by 1. So it remains as h. So what's going to happen here is the probability that you observe exactly one customer entering your cafe within a very, very short time span is lambda times h. Because so here lambda was representing per minute unit of time, but now here when I'm talking about the rate, that is not exactly per minute, right? I'm talking about the instantaneous rate. So again, this is just to give you guys some idea of how we write this lambda times h. So that will be the probability. But again, this is not the precise probability, but just an approximation. So I can maybe, so this is basically approximated probability. I'll write the actual probability soon. Okay, but now we also made an assumption. Yes, yes.
Ma'am, can you please repeat the lambda into x thing, because I couldn't hear you because of the network issue.
Oh, okay. So when I said lambda into h, let me just maybe bring that back. Yeah. So what I said was, let us say if I define my, so this is another example unrelated to what we were studying in this particular model, which is the generalized model. So here I'm defining that my lambda is 5 per minute. And now I've defined my h, which is some short time interval. Ideally, it should be very, very short, not even a minute, not even a second. But again, I'm defining my, it could, so again, the way you define short is very different. So sometimes 1 hour could also be a very short interval if you compare it to a particular year, let's say. So, but it's fine. So again, here I'm saying that my h is, let's say 1 hour. So if I say that my lambda is 5 per minute, what do you think will the same rate will be for 1 hour? So here say that it will just be 5 times 60, because I know that per minute, if it's 5, then for 1 hour what I have to do is just multiply this 5 with the number of minutes in 1 hour, which is 60, right? So this will be my rate at which I will expect some event to happen in 1 hour unit of time. So this was the rate for per minute, and using this information, I can basically say that this will be my rate per hour. So the same kind of thing I'm going to do here, and what I'm writing here is this, that, and so yeah, if you see here, what we did was 5 times 60, right? So what was 5? 5 was just the lambda value. And when I multiplied it with 60, what was that? That was the number of minutes, which was the very first definition of lambda, multiplied with the number of minutes you have within this h time period, right? So here, when I'm defining my lambda as the transition rate, I say that this is the transition rate that has the unit of time of a particular instance. So when I'm defining another time interval, which is just h, I say that there are h instances in h time period. So that is why you multiply lambda with just the h. Does this make sense?
Yeah.
Okay, good. This is very important. And again, now remember the assumption that we made. We said that within a very, very short interval of time, we do not expect many more than one. We do not expect any more than one event to occur. So the probability that this is going to happen is just 0. All right. And we know that these should add up to 1. So obviously this is just going to be 1 minus lambda times h. But again, as I said, these are just the approximated values, because again, you cannot necessarily say that the greater than 1 is 0. It is negligible, but again, there is some very, very small probability that it might still happen. But again, if you take that in the limit, so limit will be on h being even a shorter interval. So if you chop these intervals in again, very, very short time interval, and then if you again chop it, and then if you again chop it, then you see that this becomes increasingly less likely to happen. So the ideal definition is actually just to write this particular thing as O of H. And here again, because you don't know that this is the actual probability, you just add some amount of randomness to these. But again, as we know, this O of H in limit, so I can just write it here, where limit, when my H approaches 0, my O of H upon H is also 0. So in limit, these will be equal, right? And this will just be 0, because these in limits will take the value of 0, and these in limits will take the precise value that they will be taking. So this is another definition of the Poisson process. So again, I mean, what we are caring about here is the probabilities that we observe in a very, very small, a very tiny interval, right? And again, that is, and these just O of H's, these are just the second order terms, which does not matter in the limits. So this is how we will define the Poisson process, and that is precisely another definition of a Poisson process. So remember, this we are looking at the continuous time interval. So it might come to your mind that that Poisson distribution is a discrete distribution, right? But again, that distribution will be for the state space here. And what is my state space? My state space here is the number of customers that arrive. And I know that the number of customers arriving can either be 0, 1, 2, 3, right? If I'm looking at the total number of customers which are arriving. So that will be discrete. And that is why if we look at the number of customers that arrive in a cafe, this NT will follow Poisson distribution. And again, if you're looking at the time between these two customers arriving, that will follow exponential distribution. So again, remember, there is a subtle difference between Poisson process and Poisson distribution. So people are asked, you know, is there any other discrete distribution which has memoryless property? People who study Poisson process say Poisson process. And some people will remember that exponential is also memoryless. They'll say memoryless. But again, remember, Poisson process is a process. It is not a distribution. So, okay, I guess that was made clear. And now what we will study is some derivation of, basically it's just a proof that this NT indeed follows Poisson distribution. And I guess I will just go through it once. Maybe I can just, okay, let me just write it, I guess. Okay, so now I'm defining something, okay? And again, remember, so, yeah. So again, if I'm writing here NT, which represents the number of customers that arrive in a cafe in time period T, then I know that my expected number of customers arriving in a cafe at time T is just lambda times the time period, which is T, right? So lambda T will be the mean. And again, that is the variance itself because it's Poisson. So I know that that is just, you know, I mean, the expectation is just going to be lambda times T. Okay, but now what we want to do is, let us define small p j_t as the probability that I observe myself at one particular state j at time t. So again, I mean, by time t ideally, because when I'm writing nt, it shows that up until now, I have observed till t. So I am in particular state j. And again, in Poisson, I know the states will be what? 0, 1, 2, 3, right? So it can only move from 0 to 1, 1 to 2, right? And it can never even go back from 1 to 0. So we know that this is what's going to happen. And if not a transition out, it will just stay wherever it was, right? Which will be the case when you observe no customers arriving. And again, so these 0, 1, 2, 3 are J's here. So when I'm talking about state, it means a particular number of customers that you have observed up until time t, which is denoted by probability that nt is equal to j. Okay, so now we have to prove, because we already know that this should be ideally Poisson distribution, and we expect the mean to be lambda times t. So I ideally know that this should just be equal to, I'm looking at the table booklet, and instead of lambda, I'm going to write lambda t here because that is my mean here. So lambda t raised to j again, because this is the number of events, and again j factorial. So this is what you have to prove. So again, now we will try to see what do we know. Okay, so let us start. So I'm assuming that my j is 0, and there is a very, very small tiny interval h, which is also positive, so that I know that I'm looking forward in time, not at all backward in time. So now let's just say that I want to look at pj t plus h. So I'm trying to see what all can happen in this time period. So by this time period. So using this, I will just rewrite this small pjt plus h as a probability that I observe my n t plus h. I mean, by the time t plus h, I am at g. I mean, this is the number of customers that have up until now arrived in my particular restaurant. So again, now if you want to figure out the chance, so let's say this is 0, this is t, and this is t plus h. And I know that I'm at j in t plus h. So let's just say that this is the j and this is the t. So you know that to arrive in a very, very short interval at j, let's say my j is just 3 for now. So to say that I have observed 3 customers up until t plus h, I can believe 2 different sets of things, right? I mean, ideally, I can believe n sets of things, but the most probable ones will be just 2. One, that in the time period h, so in this particular time interval, there was no one particular customer arriving, or there was one particular customer arriving, right? So when I'm saying that there was no customer that arrived, so and at that point in time, I know that even at NT, I was still at the same J, right? I mean, this was still 3. But again, if I know that one customer arrived, then I will know at NT, my J was ideally 2. And then at NT plus H, I progressed to 3. So what you can rewrite this thing, what I just said is the probability that at NT, you were at J, and at NT plus H, you still remain at J, right? Because that is what you want to calculate at the end. And I can again say that this is just my NT. So I remain where I was in the previous time step, in the previous, basically the time period that I was looking at. And the next thing could also be, you know, let's say at NT, I was in J minus 1 state, and then by the time T plus H, I progressed to one additional step. So there was one more customer that I observed. And again, you know, there is a possibility that you can still go from 1 to 2 and 2 to 3 in just this particular H. But again, the chance of that happening is very, very little. And if you take the limits, that will go on. That will basically just vanish away, and that we'll see. Okay, so now if I have to rewrite this thing in terms of PJs and everything else, what will I have? So I'm saying that I was at state J by time T, but then in a very small time interval H, I still stay where I was. So the probability of that happening is 1 minus lambda H, right? Which is nothing but from here. So we observe 0 number of increments, and that and the probability of that happening is 1 minus lambda h. Ideally, I should write plus O of h, but again, because I've already written O of h here, I'm not gonna write it again over there. Okay, so I guess once I've done this, next what I'm gonna do is rewrite this thing. So again, I observe p j minus 1, and this happens by the time t, and then I observe one particular event. So the chance of that happening is lambda times h, and this OH will come as it is. So I have this thing with me as it is. And again, I mean, you won't have to remember this derivation and stuff, but I'm just doing it for the sake of it, I guess. And now we'll see what else we can do. So now what do we have? We can maybe, rearrange some stuff, and I will take the limits very soon. So what I'm going to do is now I have PJT plus H here, and I will subtract from this guy PJT. So I multiply this with 1 and this I take over there. So if I do this, what do I get here? I get PJT times lambda times H plus Pj minus 1t times lambda H plus O of H, right? So what I do now more is I divide this whole thing by H. So if I divide this whole thing by H, this H will cancel, this H will cancel out, right? And I will have one more additional H here. And now I take limits where my H goes to 0. So now if I take limit H going to 0, I'll have limits all over here. There is no H, doesn't matter. There is no H, doesn't matter. And the only thing that will matter is this particular guy, right? So I can just rewrite this particular guy as plus limit H going to 0 O of H upon H. And I know that this is just 0 because O of H converges to 0 much, much faster than this particular H guy here. And this is basically the first principal definition of a derivative. So this is in essence just taking differentiation of PJT with respect to time t, because this is t and then you just add some h. So this is kind of like the slope, right? The time is measured on the y-axis and this is states you're measuring, let's say, on the x-axis. Then you just observe the slope, the change in y upon the change in x. Okay, so this is on y and time is on x-axis. So this is the time difference, which is t plus h minus t. So that's just h. And this is the d of pjt upon dt. And now you know that this is equal to what? This is equal to, wait. Yeah, I have made one mistake. So this shouldn't, so because there's a minus here, I should have written minus lambda pgt, right? And when you take this, you will have minus lambda pjt plus lambda times pj minus 1 t, and that's it. So this is what you have. And again, this is one differential equation that you now have. But again, you have a j here and you have a j minus 1 here. So we'll have a look at how do we solve that. But again, you need not concern yourself with solving this case, but just proving that this is what works. So you will have to prove that if you use this as PJT, then this particular condition is satisfied. And again, you assume one initial condition. So we know that to figure out the constant of integration, we will need some initial condition. So I just say that my initial condition, so let me write here, my initial condition is going to be what? So again, I wasn't specifically given any condition, but I know for a fact that if no time has passed, so my Pj0, can anyone guess what will be the value of Pj0? Would anyone want to guess this? Okay, so let's just start with what does Pj0 represent? Anyone? What do you think PJ0 represents?
That there have been zero events. Sorry, there have been J events in time zero. Is it
Wait, can you say that again? I couldn't hear you clearly.
that there have been J events in time zero?
That there have been J events in time zero. Is that what you said?
Yes, yes.
Okay. So how many of you agree with what Vanshika just said? There have been J events in time zero.
The probability that there have been J events in time zero.
Yeah. I understood that you meant that. Okay, yeah. So how many of you agree with what Vanshika just said? So according to her, she's saying that we are looking at, let's say if I define my J as 3, I'm just saying that in zero time I have observed 3 customers arriving at my cafe.
So the probability should be zero, right?
Yeah, it should ideally be 0, because if I haven't yet, so my PJ0 actually represents the probability that I observe myself at a particular state J by time 0. So when I write in brackets 0, it means by time 0, which is basically the process hasn't even started yet, right? The shop isn't open yet. So the time 0, and I can't possibly be at any state, right? So there won't be any customer. So the probability of me observing myself at this J when I'm just at 0 time is 0. So I consider this as my initial condition, and this is what I will use to solve further. And again, I am not going to try to solve it, but just explain to you guys from here, which is from within your book, on how does that particular thing happen. Okay, so one more thing before we do this. Yeah. So again, how many of you agree with what I have written here? So remember the states, have I erased that? Yeah, so these are the states that I have, right? So can anyone think of can anyone think of when what I have just written on the board will not be true? So when this particular probability will not be equal to 0, what are the times when this will be the case? Anyone? So that is where the very first assumption that we built in before we derived comes through. So we assumed that my J is greater than 0. And that is the only reason I can say that the probability that I will observe myself at some state J, which is ideally greater than 0, by time 0 is 0, right? Because if I define my J to be 0, then it's ideally, what will be the probability if I define my J as 0? Anyone? P0 of 0. What will this be? So I observe myself at state 0 by time 0. Basically, I observe 0 customers entering my cafe by time 0. What is the probability of that happening?
That will always be the case, right?
Hello, am I audible? Hello. Voice is about. Hello, am I audible now?
Yes, ma'am.
Yes, ma'am.
Yeah, I guess I got cut off. Okay, still. All right. Yeah, so what I was trying to say is, did you guys hear what I was trying to say about this thing not being true always? Did you guys hear that part? Okay, let me
Yes,
just
why?
read it again.
Yes, ma'am. Because of
Okay, you
the
guys.
that is Z J greater than 0.
Exactly right. So that happens only because we're assuming that J is greater than 0. But now what will be the probability that if my J is 0, I mean, what is this? How do you guys think you can, so maybe just let me tell this in words. When I'm writing P0 in brackets 0, I'm saying that I have observed 0 customers, that is I am at the state 0 by the time 0. So what is the chance of that happening? Anyone?
See the case, right?
I couldn't hear you. Can you say that again?
That would always be the case, right?
Exactly right. Exactly, Vanshita. Thank you very much. That was great. So that will always be the case. So you know the probability is just going to be 1. So P00 is always going to be 1 and Pj0, where J is anything other than 0, is going to be 0. So this is what you have now. And again, now I'm going to use this particular thing to prove that it is indeed the Poisson distribution. that satisfies this particular equation and this particular initial condition that we have. But again, in the case of j equal to 0, you know that nothing 0 minus 1 basically exists, right? So what you will be left with is only the very first term, which, and again, if you substitute in place of j here, you will have p0t. So this will be two different conditions. So once we'll put j equal to 0, and then we'll see what happens. And then we'll see at what happens if j is greater than 0. Okay, so assuming that my j is 0, how can you define P00? So P0t is just going to be e raised to minus lambda t. Do you guys know from where I have written this? Any ideas? So what I'm now doing is, I'm trying to prove that this function satisfies this particular differential equation and this initial conditions. So now if I have to figure out P0t, basically at J0, I substitute in 0 here, which will render 1, and 0 factorial is also 1. So I get that my P0t is e raised to minus lambda t, right? And if I differentiate this thing with respect to t, what do I get? I mean, this minus lambda will come in front, and minus lambda e raised to minus lambda t, which is nothing but minus lambda P0t, which is what we expected the answer to be. So yeah, when j is 0, this equation is satisfied. And otherwise, we'll see what happens. So otherwise, I know that this is my PJT. So now we'll have to differentiate this guy with respect to t again. But we know we'll have to use some other rule, right? Because t is in the numerator. I mean, t is here as well as in the power over here, over there. So first you keep this as it is. So lambda t raised to j upon j factorial is as it is. And you differentiate this guy with respect to t. So you get minus lambda e raised to minus lambda t. Done. Next, you keep this guy constant and you differentiate this guy with respect to t. So what you get is j downstairs, and then you will have lambda t, j minus 1, right? But then again, by using chain rule, you will have to differentiate what's inside the bracket with respect to t. And over there, you will get this lambda. And the rest of the stuff will just be as it is. So e raised to minus lambda t upon j factorial. And if you try to substitute this PJT again, you get that this is nothing but minus lambda PJT plus lambda times PJ minus 1T, which is precisely the differential equation that you have derived earlier. But again, there is also one condition that we have to check, right? The initial condition, because we know that these differential equations will be satisfied by not only this particular PJ, not only this PJ, but any other PJs. I mean, there could be more than one PJs that will satisfy this particular differential equation. But not all of those PJs will also satisfy the initial condition. So we'll check whether what happens at the initial condition. So our initial condition was that I observe myself at state J by time 0 is just 0. So let's do that. So I substitute P0 here. And I do that for this particular case. And what I observe is anything raised to 0 is 1. And again, here it's multiplied by 0. So yeah, again, this is just 0. And this is 1. So 0 upon 1 is just 0, right? So I guess we have, in a way, and again, you can also check for this. And you get 1 over there as well. So hence, the boundary conditions are also satisfied. And that is how you kind of prove that, yes, it is indeed the Poisson distribution that your NT by follows. Any doubts in the derivation? Anyone? Okay, so I guess that was it. And let me ask you guys some questions now. So let us say I define a particular random variable x, okay, which follows Poisson process with the parameter 5, and I define another random variable y, which follows the Poisson process. Basically, it follows Poisson distribution. Sorry, not the process. It follows Poisson distribution with parameter 5, and this, let's say, follows Poisson distribution with the parameter 6. So what do you guys think will happen if I have to figure out the distribution of x plus y? Anyone? I think we have already seen this before, right?
Yes, ma'am. The parameters will add.
Yeah, the parameters will add up. Is that always the case? No, right? Only when I say that my x and y are independent. So given that my x and y are independent, these parameters will add up. So let me just define a very general case. I can say that this is lambda and this is mu. Then my x plus y will also follow Poisson with the parameter lambda plus mu. So again, we know that if I sum up another process that I get will be Poisson. And again, if you also look at the increments for this process or for the previous process as well. So let us say if you were looking at the increments over here, which is nt plus h minus nt, this will also follow Poisson. So even this will follow Poisson with the random variable lambda h, because that is the time that is being passed over here. Okay, so I guess that was it. And again, I guess, I mean, the another thing is also very easy. So let me just, I think we can directly go and solve the question. So in the books, they have also given a proof of why the sum of two independent causal processes is basically something like this. And it involves the MGF and blah, blah, blah. But I guess this is just, for you to do it on your own. Now let us try to solve this question. I shouldn't be seeing the solution. Okay. So let us try to read this question and we'll try to solve this. Let's see what happens. Okay. So I'll just read the question. An insurance company has two types of policies, A and B. Claims arriving under A follow Poisson process with the rate of 5 per day. So 5, and this is per day. Okay. And claims in the B, and they also follow Poisson with the rate of 3 per day. 3 per day. Okay. And now we are saying that a randomly selected claim from A has a probability of 1 upon 5 of being over 10,000, while a randomly selected claim from B has a probability 2 by 3 of being over 10,000. So something like probability of observing something from A, let's say I define my random variable as X, observed as greater than 10,000 is 1 upon 5. And the same thing for my B guy is what? 2 upon 3. Okay. Now the question asks me, calculate the number of claims over 10,000 that are expected per day. So again, it is the one insurance company that we are expected to figure this particular probability for. And they have two different kind of policies, A and B. And we are being given the respective information about these. So what do you guys think I should do next here to figure this particular probability? Just think about logic. I mean, what would your logic say? Anyone? Anyone? So what should I start off with, first of all? Can you guys hear me?
Would it be like probability of A into the probability that the claim is from A into the
Yeah.
probability that it exceeds 10,000 and plus probability that it comes from B and into probability that it exceeds 10,000.
Yeah, right. So maybe the ideal way to start this, I mean, Vanshita, you're absolutely correct. So when I have to figure out the number of claims over 10,000, I mean, the expected number of claims over 10,000, what I can do is this will just be the probability that I observe claims more than 10,000, which let's say I denote I from A, right? And again, I observe claims more than 10,000 from B. And the probability that I will observe a claim which is higher than 10,000 from A is what? So again, I know that the rate at which events occur, the rate at which the claims arrive in A follow Poisson process. So I know per day, I expect 5 number of claims to arrive. But again, out of those 5 claims, only 1/5 of the claims I expect to exceed 10,000. So this will just be 1 upon 5 plus again times 2 upon 3. So that gives you the answer 3. So you will expect 3 number of claims over 10,000 for, let's say, one particular day. Any doubts? Anyone?
No, ma'am.
And what about others? Mihir and Savi? Are you guys there? Okay. Mihir?
Ma'am, can you explain this once again? Why are we calculating this way, like multiplying the probabilities and
Okay. Okay. So again, what we have to calculate is the total number of claims which exceed 10,000 in one particular day, right? So what I'm going to do is I know that there are two types of policies, A and B, right? So I can either have a claim which exceeds 10,000, which comes from A policy, A type of policy, or it comes from B type of policy. So I know that the total number of claims which will exceed 10,000 is just the probability that my total number of claims exceed 10,000 and it comes from A, plus the probability that my total claims exceed from 10,000 and it comes from B. Do you understand this?
Yes, ma'am.
Okay, so now I have to figure out the probability that I observe a claim which exceeds 10,000 in type A policy, right? So I've said that my A follows POSVA with the parameter 5, and this is for per day. So what this essentially says is that I expect 5 number of claims to arrive per day from type A policy. But again, you're also given that not all of those claims will exceed 10,000, right? So the probability that you will observe your claim exceeding 10,000, if you're looking at a type A type policy, is just 1 upon 5. So let's say if you observe 5 claims, only 1 out of those 5 claims will be greater than 10,000. And so let's say if this was 2 by 5, so you would ideally say that if there are 5 claims in a day, then I I expect 2 out of those 5 claims to be greater than 10,000. And that is why you multiply this particular rate, which is 5, which is the total number of claims that you expect to arrive from type A policy, multiplied by the probability that you observe something which is greater than 10,000. So again, if you forget this multiplication, this is ideally what will come to your mind as well, right? So what we have to add is the number of claims, right? So even if you don't care about this particular notation, what you can just say is that my A follows POSVA with 5. So each day I expect 5 number of claims to arrive. And here I know that if I have 5 number of claims, only 1 out of those claims I expect to be greater than 10,000, right? So this is 1. So ideally this is just 1. And that is what you get here. Does this make things a bit clearer?
Yes, ma'am. Stay.
Okay, perfect. Thank you very much for asking that out. Okay, so now that this is clear, there is actually a name given to this particular thing, which is called thinning of Poisson processes. But I really don't believe in learning these names. And this is very intuitive, I would say. So again, it just says the same thing. I'm not going to repeat it again. Okay. I guess let's just continue here. Okay, so the next thing that now we are going to look at is the inter-event times. So maybe not this. I want to explain it in some another way. Okay, so this was about the adding up of the independent Poisson distributions. But again, now let us say what happens within the arrival times of event. So if I want to figure out the expected time I have to wait between 2 customers arriving at the cafe, I'll have to check what distribution it follows. We have already seen that it follows exponential distribution. So let's just kind of do that again. So again, I know that in Poisson process, so ideally, when I'm looking at the states, so let us say this is my time and this is my state. Okay, and I have some different states labeled across here. And this is, let's say, continuous time, right? So we're looking at continuous time and we're looking at discrete state. So I cannot really pin down times here. So what I can say is that from this time interval till this time interval, let's say I was at this state and then I hopped to, let's say, particularly this state. Then I hopped to this state for some big time. And then I dropped, let's say, to this particular state for this much of time. So this is how you can generally represent the states and the time intervals. But again, as we know in Poisson, you can only progress in future, right? So the states will only go from 1 to 2. There's no way you can go from 1 to 3. So again, you know that this changes happen sequentially. And that is what you have here. And you see, they haven't pinned down a particular time. Rather than pinning down a particular time, we're defining particular intervals. So T0 is first interval, T1 is another interval. And these intervals may not be of the same length, because the way I'm defining here, I'm just saying that this T0 is at state 0. T1 is the time that you spend at state 1. T2 is the time that you spend at state 2. And again, that is why you have to take these xt's to be right continuous. And that is why you have this dot here and then a line on the right of it. Because if you would have taken it here, then these T0s and this state 0 wouldn't ideally match. So I guess that's it. And this is also known as holding time. So why holding time? Because this is how much, this is for the time you expect yourself to be within a particular state. So that's basically you holding on to one particular state. So that is why this T0 is not only the inter-time event. So again, if I want to say that, what is the time spent in state 0 before I move to state 1? That will also be T0, right? In expectation, ideally. So, I mean, there are various other names and various other references that you can give to these T's. But yeah, we'll just sometimes call it waiting time. So this can also be, the time that you will have to wait in state 0 till you move to state 1. So it could also be waiting time, holding time, inter-event times, and basically other names. So I guess, again, what you're going to do here is, there is a proof that these waiting times follow exponential distribution, which again, I'm not going to cover because it's ideally just done here. So we're just going to say that this T0, T1, T2, which is the waiting time, which is the holding time, which is the inter-event arrival time, is again a sequence of independent, which is fine, exponential random variables, each with parameter lambda. So here, again, if I say that my T0 follows exponential with parameter lambda, then I know that the expectation of any exponential distribution is what? It is 1 upon lambda, right? So the expected time that I would spend in time in particular, so the interpretation of this particular thing will be the expected number of time that you will spend, and that will be your expectation of the exponential distribution, which will just be 1 upon the lambda, which is the parameter that we are assuming is constant with the lambda that we saw in the Poisson. Okay, so now that we have that, I think this is just a small proof where you kind of show that this f of t, basically the probability that you observe something less than t, is indeed 1 minus e raised to minus lambda t. And again, to do this, you figure out the probability that you observe t1 greater than t, given that t0 you're at s. So again, this is just some proof of it, which I guess is not really required. I guess this is what is much more interesting. So we'll try to solve this particular question. So let us start with reading the question first. Claims from a certain group of policies follow a Poisson process. So again, we are looking at claims, and that is our event of interest. And it follows Poisson process with a rate of 5 per day, and claims can be logged 24 hours a day. So basically, I can just say that, let's say if I denote my claims as X, it follows Poisson with the rate of 5 per day. Okay, so now I have to figure out the probability that there will be fewer than 2 claims reported on a given day. So what do you guys think I should be doing here? Anyone? I think this is fairly straightforward, right? If I want to figure out the probability that there will be less than 2 claims, I know I just have to add the probability that there will be no claims and the probability that there will be 1 claim. And if I know that my X follows Poisson with 5, so my lambda is just 5. So I can easily do these things, and I can look at my table booklet and I can see the formula. And what you will get is e raised to minus lambda times lambda raised to, again here I'm looking at 0 upon 0 factorial, plus e raised to minus 5 5 raised to 1 upon 1 factorial. And this will be your answer for the very first case. Any doubts in this particular thing? I guess this was an easy case. So let us now try to see what happens in the second question. I think this is a bit tricky. So this is asking you the probability that you will observe at least one claim. So again, when I'm talking about at least one claim, it should be greater than 1. So this is what I'm looking at. Will be reported during the next hour. Okay, so now we are given the rate in terms of per day, but now we want to figure out what's going to happen in, let's say, one particular hour, which is, so for this, what do you guys think I should be doing?
At least when it should be x greater than equal to 1.
Yeah, thank you very much. I was just checking whether you guys are paying attention or not. Thank you. That's a good observation. So yeah, at least means probability that x will be greater than or equal to 1. Good. So what else? What should I be doing next?
Convert the rate in terms of hour.
Exactly right. And how can I do that, Vanshika?
So it's given that it can be logged 24 hours a day. So rate for 1 hour would be 5 by 24, right?
Exactly right. So I can maybe define my new rate, and that will be just 5 by 24. So I know that this is the number of claims that I expect to incur within an hour, right? So again, this you can just rewrite as 1 minus the probability that you observe x less than 1. And I guess that is just 1 minus the probability that your x is 0. And because you're looking at the discrete case, right? And then what you will have here is 1 minus e raised to minus 5 by 24 and 5 by 24 raised to 0 upon 0 factorial. So yeah, this will be ideally your answer to the second bit of the question. Very well done, guys. Now the third bit of the question. Okay, so let's see what happens in this question. So we are asked the expected time before a claim comes in, given that there haven't been any claims for over a week. Okay, so even before we do this, let me just tell you guys that, let me just remind you guys that our exponential distribution has a property which is called memoryless, right? So whenever I'm saying, going back to this graph. So whenever I'm saying that I'm moving from this particular state, or let's say I don't move, I stay in the same state, it doesn't matter how much of time I have spent here. It doesn't matter how much of time I have spent here. What just matters is the chance that this is going to happen, or the chance that this jump is going to happen, right? So the probability will still be the same. So over here in the question, they say that, this statement that given that there haven't been any claims for over a week does not matter, precisely because our exponential distribution, as we all know, has memoryless property. What has happened in the past doesn't really matter much. So, does not matter at all. So the expected time before a claim comes in. So now, what do you think this will be? First of all, we have to figure out of the time here. What is the distribution of the time? Anyone? Okay, so whenever I'm talking about a Poisson process, if I'm talking about an event, the number of events, which is discrete, I know I'm talking about Poisson distribution. And whenever I'm talking about the time, which is, let's say, inter-arrival time or the waiting time or something else, I know it follows always exponential distribution. So with lambda 5, right? So it will still be just 5 as it is. And now if you were to figure out the expected time before a particular claim comes in, then what will that be? Anyone?
1 by 5 to 0.2.
Exactly right. So because my, if let's say some thing follows exponential with rate lambda, then I know that my expectation of x is nothing but 1 upon lambda. So this will just be 1 upon 5. And that will be your answer. So again, this 0.2 is in terms of days. Okay, and so you expect 0.2 days to pass before arrival of the claim. Any doubts so far? So again, actually they discuss this, and this is pretty good because not every time you will expect the memory list property to hold true. So in this paragraph, they're talking about, let's say if for a week there was no claim reported, maybe that was because there was some blockage in the system or something else. So there might be a catch-up effect the next day. So there may be, a rush of claims the very next day when, let's say, the shop opens or the system works well again. So, but again, that will not be the case always. So, yeah. So here they summarize all the definitions of Poisson process. So this was what we studied in chapter 1. This is what we studied now. This we also studied now. And again, there is one more definition which we will study soon. So now let me just come back to our flip chart and let's move forward. So I guess this was it about the Poisson process. So the very reason I'm introducing this Poisson process to you guys is because our Markov jump processes are kind of like Poisson process. So the only difference will be that in Poisson you can only go from 0 to either 0 or 1, right? And you cannot move back to 0 from 1. But that won't be the case in generalized Markov jump processes. So we are first, we've just analyzed this Poisson process and we'll see the techniques that we'll learn now implemented in Poisson process, which is a simplified scenario. And then we'll generalize it to the whole complicated model wherein you can move from any particular state to any particular other state. So I guess there is again some features that we will now discuss, and let me start with that. I guess we do have time. Let me just take 2 minutes. Yeah. Okay. So now we are going to study formally about Markov jump processes. So just to define a Markov jump process. Again, I know that it is continuous in time and state space is discrete, right? So again, discrete, and for simplification, we assume that we're looking at finite state space. Okay, so if that is the case, then my particular process, which I can define as just xt, wherein t takes values greater than or equal to 0. So this is how I can just define my Markov jump process. So again, remember in Markov chain, we used some Chapman-Kolmogorov equations to determine the probability of transitioning from one state to the other state. So it was something like the probability that, let's say at time S, you are in state I, Then at time t, you observe yourself at state j. So something like S T I J, right? And this was what? Does anyone remember? So again, I mean, if I were to rewrite this transition probability, I can maybe rewrite this as P, where I'm going from I to J, where I'm going from state I to state J. And again, what we care about is the time difference, right? Not the whole of this thing. So again, so remember, as of now, whatever I'm going to write in the bracket is the time which has been passed so far. So this will be t plus s for this particular case. So what I'm assuming is that by the time t plus s, I find myself at state j, and this t is the time that is being spent in between here. So again, okay, so maybe what you can do is you can go on looking at the question in the similar manner, and you can say that the time difference here is what? It is just t minus s. And what again you're looking at here when you try to figure out the transition probabilities is the very fact that you start at I in time s and you end up at j in time t. So I'm just going to ignore this, and what I'm going to do here is you start at s and you are ending up in time t at state j, right? So what will this be? Anyone? Do you guys remember? How did we rewrite this thing as? Does anyone remember? So this is my s, that is t, and let's say this is my 0. So the total time which has been passed up until now is this t, right? Okay. So go on. What will we do next? Anyone? So again, this is for the discrete case. I haven't yet started about Markov jump. This is the Markov chain that I'm talking about. Anyone? So do you remember what did we do? So again, what does my Chapman-Kolmogorov equation say? If I want to move from one particular state to another state in some time interval, I create something, right? I create some time interval in between this, which let's say I denote by some let's say I just denote it by h for now, and I can see that at this particular time, I observe myself at a state k. So what happens is you add up all those sample paths, right? So you first take into consideration that you move from I to k, in the, so let me just stick to the notation, from S to H, right? And then you move from K to T in time H to T. And again, because you want to do this for all of these keys, you sum it up across the keys which belong to S, which just represents that, this K can ideally take any state. Does this make sense to you guys? Do you guys remember this? I'm not getting a yes and neither a no, so I don't know what should I assume, but I'm assuming that you guys do understand what I've written on the board. So this is how we wrote the Chapman-Kolmogorov equation in the previous chapter, right? But now what I'm going to do is I'm going to redefine my notations. So I redefine notation to make it consistent with the notations that are very much commonly used in actuarial terms and the tables and everything else. So what I'm going to do is I'm going to define a new time interval now, wherein let's say if this is 0, if this is S, I define some another, so the increment is denoted by time t, so that I can rewrite the same probability. I mean, it won't be this. So now it will become the probability that you observe yourself at state j in time t s, given that you were at I in time s. Here you are again at j. So this is just redefining the notation, where again I'm redefining the way I write. I mean, just redefining what t means. Here t was the time I ended up in, and here t is basically the increment in the time, how much forward I go from s in time. So if I'm doing that, I will have x t plus s. And again, I can just rewrite this thing as also if, let's say I'm just looking at the homogeneous case, this will be P I J, where I end up, I mean the increment is T and I start at S and I move from state I to state J. So this is one way of representing the very same thing. And again, there's also another way to represent the very same thing, which is especially if you're looking at the homogeneous case, because then it doesn't matter where you start from or where you end up. What matters is just the difference, right? So what you will have here is Pij, and in bracket you just write the difference that you observe, which is just Pijt, right? And again, now if I were to write my Pijt as this big probability, I can say that this is indeed something like, the probability that I am in, let's say, state I at 0, then after t, which is 0 plus t is just t, I observe myself in state j. So this is something that you can rewrite this particular thing as. But now there's one more thing that you can do. So instead of just assuming that it is only the t time that has been passed, now I say that I want to figure out the Pij t plus s. So again, using just the same thing, what I can say is I will be summing it up across all the k's. And I think it's just easier to write the states first because it's going to be Pik and then Pkj. And here you say that I move from I to k in time step s, and then I move from k to j in time step t. So basically the timeline for this will be something like, let's say this is 0, and then this is s, and then this is So at S, you find yourself at K, and you were at I somewhere before this thing, and now you land up at J somewhere here. So you move from this particular thing. So again, ideally this should just be 0. So it basically says that you started off at 0 in state I, okay, and you move to some state K in S time period. So this is what we have written here in bracket S, which is, the time that has been passed up until now. And then you move from this S to this particular state. So here you move to J at time T plus S. So the difference is just T. So maybe what I can do is something that this S is actually not this S, but the time that you spend here, and this T comes from this, and that is just the T. So I guess this is clear. So from now onwards, whenever I'm writing Pij and then in bracket something like T plus S or something like T or something, this just denotes the increment in time, the difference in time that has been passed when I observed myself at J and from when I observed myself at state I. Is this clear to everyone? Okay, so again, now what we are going to do is we are going to use these notations to define our transition rates. And again, to define the transition rates, we have to look at transition rates from each particular state to the other state. So ultimately, we will be writing a transition matrix, similarly to the way we wrote the transition probability matrix. So if instead of the transition probabilities, if I write transition rates in that same matrix, that matrix will be known as the generator matrix. And that we'll see forward, we denote it by capital A. So we'll see that soon. But again, for now, what we are going to do is, so this again right here is the probability, right? We haven't yet looked at transition rates. We are still looking at transition probabilities. So what I will do is, let me define P of T. So this is a matrix. And this will have entries P, I, J, T, right? Where let's say, I and J will be the respective states that you move from and to. And this is the matrix that denotes, and this will be the row and this will be the column. So first row and second column of this matrix will tell you the probability that you move from state 1 to state 2 in this particular time, which is T, small t here. So now if I were to rewrite the equation that we studied here, what will this be? This will just be P of T plus S, and this will be P of S, and this will be P of T. So again, what I'm doing here is now, and again, we don't have to put this summation when I'm writing it in terms of matrix, because we know when we multiply two matrices, we are taking all the rows and all the. So writing the result in matrix terms. Okay, so remember, whenever I'm writing it in matrix terms, this is my capital P. So my capital P, T plus S, is nothing but equal to my capital P S and capital P T, right? So this is like a very simple result now for us to even interpret. And I'm assuming that my S and T both are greater than 0. So now we know that this is my transition matrix. So again, remember, whenever I say transition matrix, it means transition probability matrix, because whenever I will put rates in the matrix, that will be known as generator matrix. So again, here I'm talking about the probabilities, and this is how you get some intuitive result, right? And at least in terms of matrix terms, when you don't at least have to write IJ, which make things more complicated. So I guess this is what you do. And again, I think now there's a really big result, but let me just complete this first, I guess, where P of t is the transition matrix. Okay, so I'm assuming that this is my transition matrix. And again, this was for all the cases where you observe times greater than 0. So what happens when time is 0? Let's define. Yeah, so now I'm defining that my probability that I observe x0, which is at time 0, I observe my process to be in a particular state I. And the probability of this happening, I'm just defining it as Qi. So this is something that I have assumed. Okay, so this is the initial distribution. So basically this is just saying that you will observe yourself in state I at time 0. The chance of that happening is denoted by Qi. Yeah, I guess I was gone. Yeah, I'm back now, right? Yeah. Can you guys hear me? Okay, I'm sorry about the internet issue. What did you guys hear last? So I said that I'm just assuming some initial probability distribution where I'm seeing the probability that I observe my process in time 0 at state I is Qi. So now I want to figure out what happens forward. Given that I know all of these probabilities, given that I know all the elements of my transition matrix. So if I know where I'm starting from, then it's really easy for me to figure out where I will end up in the future states, in the future time. So 0 less than t1 less than t2, and so on and so forth. I'm just defining this as some time, a very well-defined time. And if I want to figure out the probability that I start myself at OI and then at time 1, I observe myself at J1 and so on. So at time 2, I observe myself at J2, and at time xtn, I observe myself at Gn. So the probability that this will happen is nothing but the probability that I observe myself at I. So that is just Qi right from here. And this will be multiplied with the chance that from here you move on to J1, right? So that will be P. You started at I, so you go from I to J1 in what time? So that will just be T1 minus 0. So this is just T1. And now you move from J1 to J2. So this will just be the probability from J1 to J2. And what will be the time interval? T2 minus T1, right? So this will just be T2 minus T1 and so on till you move to Jn. So this will be Jn minus 1 to Jn, and that happens in Tn minus Tn minus 1. So again, this might seem a bit complicated, but again, whenever we'll have a look at specific examples, you won't necessarily have to do it in terms of these vague Tn's and J1s and J2s and so on. So it will be much more intuitive further. But again, now we know that this is just one probability, right? That you observe yourself in a particular state I. So what you can now do is you can forget about this and you can add up all the, you can basically add up all the possible states that you can be in the state 0. So then what you will have is you will, maybe I can just write it here. So what you will have is xt1 equal to j1, comma, and so on till xtn equal to jn. And that will just be, basically you take this qi into account, but what you will now do is you will sum it up across yeah. So how far did you guys hear me? Hello.
Till the purple equation we have.
Here's the purple equation. Oh, you didn't even get the pink one or the green one.
Yeah, ma'am. From green one I did.
Okay, okay. So let me just see that again. So what I was saying is, for this pink one, what did we did? So what did we do? We assumed that we are at some particular state I in time 0, right? Which is qi. So what now I'm going to do is, I don't care where I am at state 0, right? I don't care where I start from. What I care more about is how I move forward. So what you can do is, you can pull up all the different possible values of this I that you can take at time 0 and you sum them up across. So this qi will basically be changed. So again, if this x0 is 1, this will be q1. If this x0 is 2, this will be q2, and so on and so forth. So here what I'm doing is I'm just taking into consideration the probability that I will observe my xt1. I'll observe myself at time t1 in state j and so on. So I have not written this x0 now. And what I do here is to take into account all the possible values where I can start from, again, to end up in the same similar states. I do write qi here, but then I sum it up across all the i's. So that way, and all of the, and I mean the rest of it remains the same. So again here, I'm just taking it, taking all the i's into consideration and I add them up. So does this make sense? And I think let us just end our lecture here for today. And I'll put up what's going to happen tomorrow on the Google Classrooms very soon. I think there is some internet issue now. So that's all from my side for today. So what did we study? Let me just do a bit of a recap, I guess. We studied a lot about Poisson process, right? So we studied what happens when we look at this was the notation that we discussed, that we used at the end. So we studied about the Poisson process, a new definition. And then at the end, we also studied that the inter-arrival times follow exponential distribution, and we did some sums related to it. And then we saw how we changed the notation for this particular chapter. And tomorrow we'll see what happens basically in a Markov term process. So I guess I'm going to conduct 2 lectures tomorrow. In one lecture, I think the first lecture will just be 1.5 hours of explanation of the concept. And then we will move on with the doubts. So I'll give, let's say, a 1 hour break, and we can conduct the doubt session later in the evening as well. So I guess that's it. Any doubts?